Okay, in this lecture, we are going to cover imperfect columns. So until now, we have assumed that all columns are perfectly straight. However, in real life, columns are not, or they rarely are perfectly straight. We will now consider eccentric loading instead of concentric loading. We must find the maximum stress, find the max stress, and that is equal to sigma max is equal to P over A plus max moment over I times C. So this C, this is the distance from the neutral plane to the extreme fiber of the column or the beam. C is the distance from the neutral axis to the extreme fiber. Meaning that if we have, like, let's say an I-beam looking like this, and this is then the neutral axis. Let's see that this distance, this is C. There you will find the maximum bending stress. And the same with this. This is C. And C, it can be written as I over S, where S is the section modulus. Okay, so let's look at the simply supported beam that is eccentrically loaded. Okay, simply supported beam. That is subjected to eccentrically loading. So let's draw this figure. We have pin support and we have a roller support. And we have, let's call this E, this distance, C, and this is also E. Note this as positive downwards and this as positive X. Okay, and we have this length of this beam is given as L. So we can use the beam equation. And we know for horizontally or compressively loaded beams that we have equation the fourth derivative of y plus k squared y equals 0. We have some boundary conditions. know that the flexion at 0 is equal to 0, and flexion at L is equal to 0 as well. We know that we have no moments at either end of the beam as well. So this also is a boundary condition. EI y prime prime of 0. So at 0, we will have a moment. So let's call that minus m at 0. Okay. So minus m at 0, that is equal to, well, is this P force times this arm E that goes in the this way, counterclockwise direction. So this is minus PE. In other words, y prime prime at 0 is equal to minus k squared E. Likewise, we know that EI y at L, that is equal to minus m at L. So minus m at L, that is equal to, well, that is P times this E, P times E, and that the double derivative at L is therefore equal to minus k squared E. Okay, so we have a general solution. So since we have a homogeneous differential equation, we get this. Is it A cosine kx plus B sine kx plus cx plus d. If we take this derivative of this 2 times, we get minus ak squared cosine kx minus bk squared sine kx. C and d goes away. So take the moment at 0. This should equal to minus k squared e. And we get that minus a k squared is equal to minus k squared e. So k squared goes away, negative goes away, so a is equal to e. Same we can do for y prime prime at L. This should also be equal to minus k squared e. So we get minus e cosine minus e k squared cosine kl cosine kl minus b k squared sine kl should equal minus k squared e. The k squared goes away and the negative sign goes away. We are left with e cosine kl plus b sine kl is equal to e. Solve this for b sine kl. That's equal to, if you factor out the e, 1 minus cosine al. So b becomes e times 1 minus cosine kl over sine kl. So we can update y of x. Y of x, and we get y of x is equal to, we have e cosine kx plus b, that's what we just solved for, is e 1 minus cosine kl over sine kl sine kx plus cx plus d. And we can use a boundary condition y at 0 equal to 0. Then we see that everything goes away except for e plus d. So e plus d equals to 0. So d has to be equal to minus e. Again, we can update y of x. We get that y of x is equal to e cosine kx plus e 1 minus cosine kl all over sine kl times sine kx. C is just c for now, cx minus e. We can use our last boundary condition that y at L is equal to 0. We get e cosine kl plus e 1 minus cosine kl over sine kl, but that goes away with the sine kl over there. So we are left with 1 times 1 e times 1 minus cosine kl plus cl minus e. This is 0. So we see that if we multiply this e, we get out e minus e cosine kl. That cancels with this one, and this e cancels with that e. So the only thing we're left with is that cl is equal to 0. So c must be equal to 0. So finally updating y of x, we get y of x is equal to, I can factor out e, so we get e times cosine kx plus 1 minus cosine kl all over sine kl times sine kx minus 1. Okay, we can say that 1 minus cosine kl over sine kl, that's equal to tangent to KL over 2. Plugging that into y of x, we get y of x is equal to e times cosine kx plus tangent KL over 2 times sine kx minus 1. We know that k, that's equal to the square root of p over ei. So we know that if this p goes towards infinity, so will the tangent of KL over 2. So will also k, first and foremost. So if p increases to infinity, then k will also increase to infinity. But if you take the limit as k approaches infinity of this tangent KL over 2, this will also approach infinity. And this happens for if KL over 2 is equal to pi over 2 times 2n minus 1, for n equals 1, 2, 3, and so on. So let n equal to 1, and then KL over 2 equals pi over 2, or KL equal to pi. And this we know is the critical load, pi squared EI over L squared. However, we want to check what effect E have on the deflection. So what effect does E have on the deflection? Okay, we can check the maximum deflection. So y max, that is equal to y at L over 2. We have a simply supported beam, so the maximum deflection will happen in the middle. This we know is equal to E times cosine KL over 2 plus tangent KL over 2 sine KL over 2 minus 1. Instead of writing KL over 2 all the time, I'm going to say that U is equal to KL over 2. So y at L half is equal to E times cosine U plus tangent U sine U minus 1. We can say that the maximum deflection is equal to a delta. It's not the variational operator, but it's the maximum deflection delta. That's equal to E cosine U plus tangent U sine U minus 1. Okay, this is equal to E cosine U plus, well, tangent U. That's just sine over cosine U. So we get sine squared U over cosine U minus 1. And we can put the cosine on a common denominator by multiplying by cosine up and down in the numerator and the denominator. We get cosine squared U plus sine squared U all over cosine U minus 1. And this is a trig identity. So we get E times 1 over cosine U minus 1. And we can write this as E times the secant U minus 1. So the maximum deflection, call this delta, this is equal to E times secant U minus 1. We can divide by E, so we get that secant U minus 1 is equal to maximum deflection over this E. We can solve this with respect to U. So solve with respect to U, we get secant U is equal to deflection over E plus 1, or we can say it's deflection, maximum deflection plus this eccentric over this E. Again, we can say that this is 1 over cosine U is equal to deflection plus E over E. We can take the inverse or flip it around, so we get cosine U is equal to E over delta plus E. We can take the arc cosine on both sides, and we get U is equal to arc cosine of E over delta plus E. Or if you want to use the other notation, the cosine inverse of E over delta plus E. This means that the KL over 2 is equal to cosine inverse of E over delta plus E. You can multiply by 2, and we get KL is equal to 2 times cosine inverse of E over delta plus E. We can square both sides, and we get that K squared is equal to 4 cosine inverse of E over delta plus E. All this is squared, and we can divide by L squared. We know that K squared is equal to P over EI. Then we can solve for PCR. PCR is equal to 4 EI over L squared times cosine inverse of E over delta plus E squared. We can see that if this E is equal to 0, the only thing we get is PCR is equal to 4 pi squared EI over L squared. Okay,